3 in here, and the water must be pumped from a pond to an open discharge 40 feet above the pump. So that is the static head from the pump to the discharge. So basically in this finger, it measures from the pump to the discharge point in there in terms of the height. And then the line from the pump to the discharge consists of 340 feet of 4-inch pipe equipped with the check valve, one check valve, and 3 standard elbows. So that is the fittings. We need to determine the equivalent length. So that here, basically, the pipe from the pump to the discharge, and that for the problem, 4-inch pipe and 340 feet long. And then the pump is located 10 feet above the pond water level. So that is from the water level that we have here. Water level, the pump about 10 feet above the water level. So that problem given. The intake line consists of, so from the intake to the pump, just something like that. The intake to the pump, and that is given 10 feet. The intake consists of 20 feet hose, 4-inch diameter, and equipped with a foot valve. So the question asks is, find the total head that pump must be produced for a flow of 280 gallons per minute, and the equivalent length of the foot valve equal to 7 feet. So they already give us the equivalent length of the foot valve. We just only need to determine the check valve and the standard elbows equivalent length. So it always starts with the equivalent length for the fittings before we apply for the table 9798. So one check valve, 20 feet. Do you know where to find that out? By now, if you watch lesson video in problem 2, you can be able to determine that. Let me go one over again in this case. Go to finger 9-4 and the check valve. Look for check valve, and the nominal diameter is 4-inch. Then we can be able to find that down. So let's do one more time on that finger. So we have 4-inch nominal. See that? And then the check valve, where the check valve here. The check valve. Then draw a line, straight line between that, the intersection in the middle line, and that is about 25 feet equivalent length. And then they have another is standard elbow here, and also 4 feet. So we draw the line there, and the intersect of this line is about 11 feet equivalent length. So from that we can be able to find out the check valve 25 feet to show you, standard elbow 11 feet, but 3 of them, so 33 feet. 1 foot valve they already give us in the problem, so we can have the sum of the length including the length of the pipe and the equivalent length for fittings, check valve, standard elbows, and 1 foot valve. So it will be 340, which is the pipe itself, equivalent length for the check valve, just determine, standard elbow for 3, and 70 for the foot valve. So we have total for 68 feet. That's similar to we do in problem 2 for compressed air. Then friction head, using table 9.7 at 280 gallons per minute, we can be able to determine what is the friction head. So basically the pressure drop go through this length and the fittings, and that is 5.4 foot for every 100 feet. So 5.4 feet. friction head required for every 100 feet of equivalent length. So with that, let's go to that table, see how it goes to that here. So for the pipe, go to that table for the pipe, and we need to determine the volume. So it's 280, so as you can see 280 is somewhere near there, and the diameter E4, so with 275 it will be 21, it will be 5.2, and you can see, and the 300 it will be 6.1. So you do some interpolation, then you can be able to determine 5.4 for 2.8 gallon per minute. So that friction loss in the pipe, similar to problem 2, we have total equivalent length including the length of the pipe 468. This measure for every 100 feet of the pipe, so you have divided by 100, friction loss 5.4 feet, so you will have the friction loss through the pipe, and the fitting is 25.3 feet. And then we, after the pipe, we talk about the hose. Head loss in hose, we use table 9.8. Similarly, for hose, we can go to table 9.8 in here, and we also look for 280. So you have 275, 380, and the diameter is 4, so it's somewhere 4.2 and 4.9, and that is interpolate again. Then we'll be able to find out that is 4.3, and then for every 100 feet of the hose, so the hose only 20 feet that given in the problem, 20 feet hose, then we can be able to determine the head loss in hose 0.9 feet. So that static head given 40 feet above the pump, from the pump to the discharge 40 feet, and then 10 feet from the point to the pump. So the static head, only the water, in terms of geometry for the water is 50 feet. Total head is equal to static head plus the friction loss through the pipe, through the fittings, and through the hose. Through the pipe and fittings 25.3 feet. Through the hose 0.9 feet, 76.2 feet. That is the minimum head needed for the pump. And when you get the minimum, go to the second question they asked. With that total head, we already determine the minimum size of M-rated centrifugal pump required to pump 280 gallons per minute through the system. So from that one, we can be able to use the table 9.9, but before the 2 input, very important. What is the height of the pump above the water level? The problem gives 10 feet. And the required total head, we just determined in the previous section, 76.2 feet. Then we go to the table here, go to the table 9.9. So go back here, 10 feet above, and required total head is 76. And the gallon have to be at least 280 gallon per minute. So keep that in mind when we're looking for there. So let's go take time to consider. So height of pump above water, so this is the column 10, and then the head loss is the model 5, not enough. We need to have 76.2. That's not enough. This is only 70. That is head loss 70, and for 10, 76. So somewhere between here. That here the minimum capacity only can produce less than 66 gallon per minute. We need 280 gallon per minute. Model 8, not good. Model 7, not good, not enough. We need 76 at least. This one, in terms of the total head, that's good, but it's not enough for the capacity 280. Similarly, keep going, go to model 80. let's go to model 18 first. The next one is uh, 20. So you have here 70 and 80. The capacity for 10 feet of the pump above the water is only get somewhere 200 gallon per minute. We need 280, not good. Similarly, 18, not good. Go to 40, then it between 70 and 80, we have 76.2 total head, and then the pump is 10 feet above the water. Then the capacity, the minimum we get is somewhere between 465 and 535, and that meet the demand because the minimum we get to pump is 280 gallon per minute. If you go further, of course, it have higher volume, and we don't need that because that will consume more energy, not efficient. So that's why we choose the model 40, and then we can be able to determine the capacity by interpolate. If it's 70 head loss, so it's 5. If it's 70 total head, then we can have the 70. Then we have 535 gallon per minute. If it's 80, 465 gallon per minute, and we need is 76.2, so you can interpolate that to determine the last answer for the question capacity. When we choose that, so we do the interpolation for this is for 70 total head, 465 is for 80 total head. We have 76.2 feet total head, interpolate, so we will determine the capacity is 492 gallon per minute if we choose model 440M. So with that,